Okay, everybody, welcome. My name is Mike Zephyr, and I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne. And this is a talk today by Madeleine Udell from Cornell University for the Quantitative Methods Network, or QMNet, here at the University of Melbourne, which is kind of an internal and relatively informal network we have of and for and by quantitative researchers. And so Madeleine very kindly has agreed to talk to us today about missing data and missing data imputation in low-rank models. And so let me introduce you, Madeleine. So Madeleine Udell has a BS in mathematics and physics from Yale and a PhD in computational and mathematical engineering from Stanford. And you had a postdoc at Caltech, which is such a beautiful part of California. She's now
right now the whole thing's on fire, but
oh, that's great. Normally it's great. She's an assistant professor now of operations research and information engineering, and the Richard and Sybil Smith Sesquicentennial, I'm not going to be able to say that properly in the introduction, I should practice, fellow at Cornell University, Sesquicentennial. She studies optimization, machine learning for large-scale data analysis and control, and your work in optimization centers on detection and exploiting novel structures in optimization problems with a focus on convex and low-rank problems is really great. These structures lead the way to automatic proofs of optimality, better complexity guarantees, and faster, more efficient, more memory efficient algorithms. You've got a package for the Julia language, and your work on generalized low rank models, or GLRMs, extends PCA to embed tabular data sets with heterogeneous types of data in a low dimensional space, providing a coherent framework for compressing, denoising, and imputing missing entries, which is what you're going to be speaking to us today about. So with that, I'll hand it over to you, Madeleine, and just, again, thank you so much for doing this. We really appreciate it, all the way in Ithaca.
Great, so it's great to be here today. I have to say it's a real pleasure to be able to give a talk in Melbourne and yet, have dinner with my family. I looked up briefly the fare, the fares on Google Flights, and it looks like it would have taken me at least 27 hours under the best conditions to get there. So I think this is a wonderful format. I hope this continues post-pandemic. I should apologize for my somewhat spectral appearance because it's night here, but so it goes. Okay. Great. So I'm going to tell you a little bit about how to impute missing data using low-rank models and some techniques to go beyond low-rank models. And generally, I welcome questions. I love seeing people's faces. I can't see your faces, so I think you're going to have to, indicate, what you're interested in to Michael via the Q&A, and then it'll help me direct my talk and make sure that I'm directing it towards what you guys are interested in, since you're a large group that I haven't chatted with before. So it's great to be here. Good. Let's get started. Okay, so here's the kind of problem that I had in mind. And actually, the first place that I saw this problem was when I worked as a data scientist on the Obama 2012 campaign. And so we had this data table that looked kind of like this. We had one row for every registered voter in the United States. So that was about 300 million rows. And we knew a bunch of things about each of these people. So maybe we knew their age, their gender, what state they lived in, their income, their level of education. And actually we knew a bunch of other things, right? It's very easy to buy extra information about people. There was also lots of information recorded about whether or not they had voted in many of the past elections, etc. One thing, so actually the initial assignment that my manager gave me on this campaign was to cluster these people. Okay, and you start looking at the data and you say, well, there are some problems if I wanted to cluster these people, right? What does it mean to cluster these people? Well, to cluster, I need a distance metric, okay? And so I would need to be able to compare things like, the distance between being age 29 and age 57 versus the distance between being male and female, versus the distance between living in Connecticut and New York, versus the distance between being, having finished a college education versus a master's degree. Okay, so I need to, okay, so how would I compare these things? What, does that even make sense? Not to mention the fact that there's some missing values. Like here we see that we don't know the age of this person who lives in California, or we don't know the gender of this 57-year-old from New York. So a lot of sort of basic data science workflows become challenging in this setting, okay? So how would we do things like detect demographic groups automatically from data, find typical responses within these groups, identify related features, and impute missing entries? I should bring up a meta point, which is it's not even clear that it's reasonable to impute missing entries. Most of my talk, I'm going to assume that it's a reasonable thing to do, but perhaps the reason that this 57-year-old in New York did not write down their gender is because they don't believe that the gender options given are valid for them, right? So, okay, but I'm mostly going to proceed assuming that imputation makes sense. Okay, so more generally, let's imagine we've got a data table. Data table consists of m examples. These are the rows in the table, who might be patients in a hospital, respondents on a survey, or even assets in a financial model. And we've got n features, things that we know about them, like their results for a certain series of tests, answers to questions, or performance indicators for financial variables. So the ith row of this matrix A is going to give the feature vector for the ith example, and the jth column will give the values of the jth feature across all of the examples. Okay. So in general, one cannot make progress without assumptions. So for the bulk of this talk, here's the assumption I'm going to make, and I'm going to help justify to you why this is a reasonable assumption later in this talk, both through examples and also through a little bit of theory. And then at the very end of the talk, we're going to see if we can poke some holes in the assumption and see ways that we can improve upon it, okay? But here's the assumption. We're going to say that for a given data table A, we're going to assume that it's well approximated by a low-rank matrix. So here's what I mean by that. I'm going to assume that there's a skinny matrix X and a fat matrix Y, so that when I multiply X times Y, okay, notice that if I multiply X times Y, X is a real valued matrix with K columns, Y is a real valued matrix with K rows. The result is a real valued rank K or lower matrix. Okay, but I'm going to say that X times Y is approximately equal to A. Okay, that there is an X and a Y, so X times Y is approximately equal to A. Okay, now it's not totally clear what approximately equals means, right? Because this thing on the left is a low rank matrix, and this thing on the right is a data table with heterogeneous types and missing values, okay? The entries could be ordinal, they could be categorical, they could be Boolean, right? Who knows what they could be, okay? So I have to do some explaining about what squiggly equals means. But once we figure out squiggly equals, then we're in good shape. Because what it means is that there's a row of X for every example. So for example, for every voter in the United States. And there's a column of Y for every feature, for everything we know about them. And this enables us to answer all the questions that we talked about before. Right? So you can think about X and Y as being a compressed representation of the data table A. That's kind of nice. You can think about the row of X or the column of Y as being points associated with example I or feature J. And you can do imputation by noticing that the inner product between the ith row of X and the jth column of Y will then approximate the ijth entry of A. Okay, if this squiggly equals relation holds. Okay, so why would we be doing this? I should also mention that you could cluster the rows of X, right, in order to cluster the people in your data set. Right? You could cluster the columns of Y in order to cluster the features in your data set. Okay, so you can do a lot of these kinds of, basically, like, data science becomes possible. Okay, so why would we be doing this? One reason might be to reduce storage. Another might be to understand your data, to visualize or cluster it by visualizing or cluster the rows of X or the columns of Y. You could be doing it to remove noise. Maybe you think that X times Y is actually a more faithful representation of the underlying phenomenon than the data A that you measured. You might be doing it to infer missing data. And you might be doing it to simplify data processing. Maybe you're going to use the rows of X as representations for, say, voters in your cohort, and do all your subsequent data analysis using those vector representations, which are really nice to work with because they're complete and they're real valued and they're short. Okay, so suddenly everything becomes easier. Okay, so the simplest version of a low-rank model is one that probably most of you have heard of, which is principal components analysis. So principal components analysis looks like this. If A were a real valued matrix that were completely observed, PCA says, I want you to minimize the sum of squared errors between A and X times Y. Okay, or we can write that entry-wise as AI minus XIYJ. Here, XI is a row vector. Okay, so XIYJ is an inner product. That's a number. Okay, so why would we do this? Okay, I mean, a lot of people, you get used to just seeing this square pop up everywhere, right? The squared error pop up. You stop even seeing it. Okay, but why would we be using the squared error? Why would squared error measure what we mean by approximately equal to? Okay, and probably the best reason, certainly the original reason, is that it gives you a problem that's a lot easier to solve. Okay, and as a result, people have been solving this problem for over 100 years. Okay, so Pearson first proposed this in 1901. Hoteling coined the name in 1933. You could think of it as least squares low rank fitting. Okay, so I would almost call it analytical though. Okay, Speedy is not quite analytic. Solution uses the singular value decomposition of A, or equivalently the eigenvalue decomposition of A transpose A. You just take the top k eigenvectors and use them to reconstruct X and Y. But I want to point out that there's another solution, which is maybe even easier to see, which goes like this. Pick a guess for Y and minimize over X. That's a least squares problem. It's actually a m different decoupled least squares problems, one for every row of X. Okay, now fix that guess for X and minimize over Y. Again, it decouples into n distinct least squares problems. Okay, so if we know how to solve least squares, we can do this, right? We minimize over X, minimize over Y, minimize over X, minimize over Y. We could repeat this and we might ask, does it, do we get the same answer? Okay, and the answer is yes, unless you were extraordinarily unlucky in how you initialized Y. Okay, so with probability 1 over initializations of Y, that converges to the same thing. Okay, it's a pretty easy problem to solve. Okay, now it doesn't quite solve our problem because it doesn't handle missing data and it doesn't handle heterogeneous data. Okay, so let's see how to fix it. So there are a couple of generalizations that we're going to make in order to allow this framework to handle the more general problem. Okay, so the first change that I want to point out is that instead of minimizing the loss over every entry in your data table, you just minimize it over the entries that you've seen. Okay, so I'm just going to minimize it over I, J in this index set omega. Those are the set of entries of A that I've observed. Okay. The second change is that I'm going to introduce a loss function LJ. So rather than blindly use a square loss for every piece of data, instead, I'm going to say LJ is a loss function that depends on feature J. Okay, so I might have a different one for real valued entries, a different one for Booleans, a different one for ordinals, a different one for categoricals, right? And I could even design a specialized loss LJ for my particular kind of data if I happen to know something about it. Okay, so this LJ, it's going to measure how angry I am to have approximated the observed value AIJ by the number XIYJ. Okay. And the third thing that I'm going to do is I might add a little bit of regularization on X and on Y. And this is just going to ensure some kinds of stability of the solution. It's useful for proving theorems. The most common regularization that you might add would be quadratic regularization. That's useful even if you don't care about proving theorems. Other kinds of regularization you might want would be encourage sparsity or other kinds of structure in your solution if you want to be able to interpret the X and Y that you get at. Okay, but for the most part, we'll be talking about just this minimizing the loss functions problem. Now, once we've made these changes, unfortunately, the problem is NP hard to solve exactly. Okay, so, you know, abandon all hope. Okay, no, don't abandon all hope, because we can still approximately minimize this. Okay, so in fact, essentially the same, right? So the exact solution does not generalize, but alternating minimization does. You can still fix a guess for y, minimize over x. Again, the problems decouple over rows of x. And in fact, if the loss functions are convex and the regularizers are convex, all those problems are convex and easy to solve. Okay, now you fix that guess for x, you minimize over y. Again, the problems decouple over columns of y. That's really useful for parallelization. Okay, right, so you can solve the problem, right, so you minimize over y, and you repeat, minimize over x, minimize over y, minimize over x, minimize over y. Now, you cannot guarantee that this finds the right solution, but in practice, it usually does pretty well. Okay, there are also tricks for initializing, so it does even better. Okay, it's a pretty robust method. Okay, so let's talk about some places that you could use this. So I'm not going to say much more about optimization, but I am by training an optimizer. So if you have any questions about this, I love them. Okay. Okay, so how would we use this kind of technique? Let me show you sort of the simplest place that this comes up, which is a problem that's now called matrix completion, where you observe aij only for ij in some index set. And here we're going to assume that aij are real valued. Okay, so the matrix completion problem, as it's usually written in the literature, there's some variants of it, but one of the most common variants is this one. You say, I'm going to minimize the difference between aij and xiyj, measured in the squared loss sense, plus some quadratic regularization on x, plus some quadratic regularization on y. So what's kind of interesting about this is if you contrast it to, you know, what you would otherwise be doing. Okay, so imagine that you had a data table A that was real valued, and there were just a couple of entries missing. You might be tempted to just delete the rows that had missing entries. Okay, and what matrix completion is saying to you is, no, you don't have to delete the rows that have missing entries. You're throwing away perfectly good data if you do that, right? All the other entries in those rows were observed, and you should take advantage of them. Okay, so it turns out that you don't need to waste your data. You can borrow strengths from the entries that are not missing. But more surprising is the fact that even when most entries are missing, matrix completion still works. So you can be in a setting where every row has missing entries. Okay, and you can, you know, complete the matrix. You can essentially do PCA on that same matrix. Okay, so this is pretty cool. Okay, so you can you can push this a little bit farther. You could say, well, what if I have, you know, right? We know that the squared error loss corresponds to Gaussian noise, right? If I thought that there was, you know, I had observed my data with Gaussian errors, it would be a reasonable loss function to use. It's the negative log likelihood of that noise distribution. Okay, similarly, if I thought I had a heavy-tailed noise, Laplacian noise, right, maybe I should be using an absolute value loss function. If I had Gaussian plus Laplacian noise, you can actually show that the right sort of negative log likelihood is something called the Huber loss, which is, it looks like a quadratic for small values of its argument, and then it goes linear farther out. If I had Poisson noise, right, count data, I should be using the Poisson loss. If I had Bernoulli data, I should be using the Bernoulli loss. Okay, so I can keep going. In fact, I can prove a theorem for each of these that says that sort of maximum likelihood low rank estimation works. Okay, so we can collect actually a large number of losses, and here I'm showing you actually a bunch of loss functions, all of which exist in the Julia library low rank models. Okay, so if you want, you know, you can pick loss functions that are really adapted for your problem. I have ones that, you know, I've developed and I really like. The particularly complicated ones, so, you know, quadratic loss, L1 loss, Huber loss, pretty standard. Hinge loss and logistic loss are pretty standard for Booleans. Things get more interesting when you get to ordinals and categoricals, so I'm not going to have time to tell you very much about them, but I would really strongly recommend the bigger versus smaller loss for ordinal data, or the one versus all loss for categorical data. The multinomial loss is also nice because it has a probabilistic interpretation. So it means that if you want to fit your model and then sample from your model, for example, to do multiple imputation, it's very easy to do that with the multinomial loss. Okay, so all sorts of losses. Regularizers, probably slightly less used, but they can be used to impose structure. So for example, you can ask for quadratic regularization in order to reduce the norm of your model. It often makes it more statistically stable. You could ask for one norm regularization. That tends to make the entries of X and Y sparse. You get a bunch of zeros, which can help with interpretability. Similarly, the non-negative constraint, it enforces that the entries be greater than or equal to 0, which helps with interpretability. And finally, I want to mention another interesting combination of regularizers. You can ask for the entries of X to have exactly 1, 1, and the rest zeros, and put no regularization on Y. And if you do alternating minimization on that objective, it reproduces Lloyd's k-means algorithm. Okay, so because I can mix and match with the losses, now for free, I get k-means equivalents for any data type I want. Okay, so this is pretty cool. It's like immediately I get to generalize k-means to, you know, ordinal data or Bernoulli data or right, whatever it is, multinomial data. Okay, so it's kind of fun. Okay, so this Julia implementation is called low-rank models. It has all these loss functions. You can choose between them. You can decide exactly what you want, or if you don't want to make any decisions, we've got some default loss functions and regularizers for you to use, and you can use those to fit a generalized low-rank model in 2 lines of code. You say, please give me a generalized low-rank model on my data frame with rank 5, and then you fit it. And it'll give you the X and Y. You can also call, you know, impute or impute missing, and it'll impute the missing values. Okay. So pretty, we tried to make it easy to use. Great. Okay, so let me show you how to use this to impute missing data. Okay, so now if we want to impute missing data and our data has heterogeneous types, we better make imputations that are of the right type. Okay, now X times Y is a number. It's not of the right type, unless, you know, we've got numerical data. Okay, so to impute the most likely true data, we again rely on the loss function. The loss function is the thing that connects real values and the kinds of values that we've observed, right? So to fit the model, we minimize over X and Y. But to do imputation, right, we fixed the model, the X and the Y. And what we do is we minimize over the other argument, right? The argument that, you know, should be in the right domain. Okay, the value that we didn't observe. Okay, so we're going to minimize. So if we want to impute the ijth entry, we minimize the jth loss function, fixing xi, over the possible values of the observation. So we find the most likely observation given the parameters. Okay. So there's an implicit constraint that the imputed data has to lie in the right space. It has to be in the domain of this loss function. Okay. And the domain might be integers or positive integers or whatever it is you want.
So
okay,
Madeleine,
so yes.
Sorry to interrupt. We've got a
no, I love questions.
Okay, great. We've got a question here from Nicholas, who's asking if the imputation method implicitly assumes missing at random, or missing completely at random, I guess.
Yes. So I always think this is an interesting way that people phrase this question. So the imputation method does not assume anything. Now, if I wanted to prove a theorem, then I would need an assumption. But I haven't shown you any theorems. Okay, so I don't need any assumptions. Sorry, so that's a glib answer. If you want to prove theorems about recovery in these models, you almost always need missing completely at random. Almost all of the theory assumes missing completely at random. Now, the low-rank structure is it's quite constrained. It's actually very constrained. And as a result, you can even show really some kind of interesting theorems about recovery for deterministic sampling patterns. So you can show things that are actually much stronger, but I'm not aware of any sort of very good results for missing at random. Certainly missing not at random, you can do pretty horrible things that will mess it up. But it's actually pretty hard to mess up. I'm going to show you some models at the end of the talk that are very easy to mess up. But this one, it's pretty robust to different missingness patterns. Okay, good. Okay, right. So if we impute and our loss function is quadratic, L1 or Huber, then actually the imputation matches xi, yj. It's really only if the domain is something else. So for example, if the loss function is hinge loss, so that means the domain of that second argument is say plus or minus 1. In that case, the imputed value matches the sign of xi, yj. So this is kind of reasonable. If xi, yj is positive, you get a +1. If xi, yj is negative, you get a -1. Okay, so and then you got some mapping between you know, plus and -1 and the Boolean labels that you care about, like male, female. Okay. Okay, so let's see how well it works. So this is a synthetic data set, but I'd like you to imagine this is a data set that comes from a hospital. Okay, so we run a hospital information system, and we have collected test results for many patients. So each row here is a patient on a variety of different tests. So we've got 3 different batteries of tests. The first one gives numeric results. That's the first cluster of columns, and you can see the numbers represented as these using this color scale. Okay, so you can see that there are many different kinds of numbers in this chunk of columns. The next chunk of columns gives Boolean, right? Tests give Boolean results. So maybe these are actually diagnoses. You know, yes or no, do you have heart disease? Yes or no, do you have lung cancer? And then the third chunk of tests is on an ordinal scale. So perhaps we've asked the patients, tell me your level of pain on a scale from 1 to 7. Okay, how strongly do you agree with the problem? You know, with the following you know, statement. You know, 1 very strongly disagree. Okay, so 3 different kinds of data, but we've had a terrible problem, and our hospital information system has lost the values for 2 of the kinds of tests for half of the patients. Okay, this is very embarrassing, and so of course, rather than admit it to the patients, we're going to impute the data. Okay, so here's one way that we could do it: is we could just use quadratic loss functions. Okay, quadratic loss functions for everything. Okay, leaving out the missing entries. So we're not gonna, we're just gonna do a sum over the entries that we observed of the error, you know, the square of xi, yj minus aij. If we do that, here's the recovery. It actually looks decent. And you can see the error here. So green here is 0 error. Yellow is unit error. So you can see it's like mostly green. It's actually doing a decent job. Yeah, notice here I'm showing what the imputations would be on the data that I've observed. Now, of course, I don't actually need to impute that data, so you don't have to worry too much about that. Okay, but if I use loss functions that are adapted to the types of data, so I'm going to use Huber loss for the real values, Boolean, hinge loss for the Boolean values, and ordinal hinge loss for the ordinal values, suddenly the error goes down by almost a factor of 2. Okay, you can see actually it improves particularly on the real value data, but even over here I get much better results. Okay, so using a loss function adapted to the data can really help. Okay, so how do we validate the model? We've got some parameters to choose, things like the rank of the model K and the regularization parameter lambda. How do we choose those things? Well, a standard approach is to leave out 10% cross-validation. Leave out 10% of the entries. So add extra missing entries into your data and use the model to predict them. Okay, this allows you to choose the model parameters that best predict your data. Okay, so here I'm showing you an example. This is a synthetic rank 3 data set. So you can see rank 1 doesn't fit it very well. Rank 2 fits it a little bit better. Any rank greater than 2 fits it pretty well. And in fact, the only problem that happens, I mean, as you go up in rank from 3, which is brown, to 4, which is these asterisks, to 5, which is the diamonds, the fit gets a little bit worse if you don't add regularization. If you add a little bit of regularization, you can improve the fit for the higher rank models. But the best fit is achieved by getting the rank exactly right and using 0 regularization. Okay, now here, this is another place to answer the question of like, what's your missingness distribution? So if you have a guess at what the missingness distribution of your data is, you can do this sort of cross-validation procedure, leaving out entries in a way that you think is consistent with the missing model that generated your data. Okay. And so then you can assess, how does your model do at imputation when the missingness pattern is, what you think it is. Okay, so if you have a model for the missingness, you can do pretty well. Okay. So let me show you so this is now a real data set that really looks very similar to the hospitalization example that I showed you before. So this is a hospitalization data set. It comes from Stanford Hospital. It has about 1 million patients in it. And one row of this data table is a single hospitalization. So for that hospitalization, we know the patient's demographics, we know what diagnoses were made, what procedures were done, and we know what comorbidities the patient had associated with them. Okay. Now, if we try to leave out some entries and impute them, we can look and see how well we're able to impute those missing entries. And what I want you to see here is as the model rank increases, the error of those imputations goes down, and it goes down faster if you use, so this yellow line is principal components analysis, so quadratic loss. It goes down much faster if you use a loss function that's adapted to each kind of data. Okay, so again, hinge loss for the Booleans, ordinal hinge loss for the ordinals. Okay, so in fact, we observe exactly the same phenomenon that we did before in the synthetic data, that the fit gets better using a tailored loss than using the untailored loss. Interestingly, if you go for a very, very low rank model, it doesn't really matter. If you allow a higher rank, then you do better using the tailored loss. Okay. It's also worth pointing out that this data set doesn't look like very low rank, right? The error keeps improving as we increase the rank. Okay. Multiple imputation. So since you guys do quantitative methods, I assume that means you have several social scientists among you. So multiple imputation is it's a really popular modality for data imputation in the social sciences. And the reason is because you can use it to model the uncertainty due to data imputation. So the approach is you impute the data many different times, so many different draws from some model, and you can fit whatever you want on top of that sort of completed data set. So now you have like 20 different completed data sets. You fit your statistic of interest, and you look at the distribution over these different imputed data sets in order to get a sense for how much the missing data has affected the uncertainty in the final statistic of interest. Okay, so there are lots of different models for multiple imputation. In the social sciences, I think some of the most popular ones are Amelia 2 and mice. So you can also use generalized low rank models for multiple imputation. You do need to use probabilistic loss functions for which it makes sense to ask to draw a sample from the posterior. So these are things like logistic loss instead of hinge loss, or multinomial loss instead of the one versus all loss. Okay. So if you were going to do just one imputation, you would impute with a conditional mode, and that's actually exactly what I showed you before. But if you wanted multiple imputations, you can do that with random draws from the conditional distribution. If you want to do even better, what you might do is bootstrap over the observations from your model and refit the entire generalized low rank model, and then do a random draw from that conditional distribution. Okay, and that does provably that gets you sort of consistent multiple imputations. Okay, so if we compare this to Amelia, so we're gonna compare the error in these imputations to the error in Amelia's imputations over several different versions of a generalized low rank model, and on average they outperform, okay, by a substantial margin. And then ditto for mice. I think the mice is doing a little bit better here than Amelia, but not a lot. And part of the reason for that is because the generalized low rank model has a consistent a consistent view of what's going on in this data set, whereas mice is doing things iteratively. It makes it both hard to converge, it takes a long time to converge, and it's not even clear that there is a limit distribution. Okay, great. Let me tell you a little bit. Oh, sorry, do you have more questions?
Yeah, there are two questions that came up. One is your GLRM package available in R?
The GLRM package is, so here's the way to use it if you're in R. There's an H2O implementation of generalized low-rank models. H2O is a large-scale machine learning framework, and they have an R front end. So if you're married to R, then that's the way to use it. But I'll also point out that R and Julia are extremely interoperable. You can call Julia from R, you can call R from Julia. There are packages in both languages to do this.
Right.
And if you want to use a Jupyter notebook, then you can just write R in one cell and Julia in the next cell, and no one will be the wiser.
Right. Okay, and then Sybil is asking, what if we have labeled data? He says, I mean, for the super.
Sorry. Also, actually, I want to say something about. So this is I'm going to do 30 seconds of Julia proselytization. The reason why there's not an R version is because if you wrote this code in R, it would be extremely slow. I'm going to say the same thing about Python. You can't write this code in Python, it would be extremely slow. If you wanted to have a Python version or an R version, what you would end up doing is you would write the actual workhorse code in C, and you would have an R wrapper or Python wrapper for it, okay? Julia is different. The front end looks as easy to use as Python or R, but you can write the code for your optimization procedures in Julia, and it's still fast. Okay, so this is kind of the magic of Julia, is it goes all the way, you can get high performance in a language that looks like a friendly scripting language. So the nice thing about that is, if you learn Julia, you would be able to read my code, you would be able to modify the algorithms, or not, right? So that's kind of fun. You don't have to move to C in order to do things that are actually performant.
Understood. Yeah, feel free to preach on any topic. It's okay. So, and then the next question is, what if we have labeled data? And he writes, I mean, for the supervised learning, do you use the labels?
Yes. So essentially everything I've been talking about so far is unsupervised learning, right? I'm saying I'm going to do imputation. Now, if you have a supervised learning problem, I mean, there's several ways to go, right? So you say, so are you saying, I've got missing values in my features, and also I want to do supervised learning? So I mean, okay, there are lots of supervised learning approaches that don't mind missing data, right? You can use a random forest. There's even ways of doing this with deep neural nets. But if you wanted to use a linear model, then yes, you're in trouble, and you need to do some data imputation before you can do your supervised learning. Now you can, so you could just do imputation first, right? And then supervised learning. That would be fine. Note that low-rank models, the generalized low-rank models framework, is doing simultaneous imputation and dimensionality reduction. Okay, so you could use the sort of low-dimensional vectors X instead of using the imputed data to do your subsequent predictions. And that often is actually going to work better if you're in a linear models framework, because you've gotten rid of some of the non-linearity in your observations and actually denoised your observations. Okay. But a third thing that you can do is you can say, I want to do some combination of unsupervised learning and supervised learning. Like, I want to do imputation, but I also want to capture a subspace that's relevant to my prediction. And so if you want to do that, you can actually just append your labels as another column to your data frame. And what you would do is you would make so each of these loss functions, right, you get to choose whatever loss functions you want. You can make the weight of the loss function that corresponds to your label as high as you want. Okay, so as you make that weight higher and higher and higher and higher, you're going to be converging towards just solving the supervised learning problem. If you make that weight lower and lower and lower, you get towards you converge to the unsupervised learning problem. So that's actually a very interesting approach. There's some theory on, and basically what you're doing is you're adding in unsupervised objective plus supervised objective in this linear modeling sort of framework. Both are sort of generalized linear models, and you're simultaneously minimizing them. And really your only parameter is just this regularization parameter of, you know, how much do you care about the supervised objective versus the unsupervised objective. There's a kind of interesting paper that was recently published in the Journal of the American Statistical Association called Embedding Learning, which discusses some theory on how well that kind of approach works. And yeah, super cool numerical example. So if you want to, so that's also a very reasonable approach.
That's great. Thanks.
Okay, great. Okay, so we have time for probably 2 of these 3 sections. So automated machine learning, why should so many data sets be approximately low rank, or how to move beyond low rank models for even better fits, particularly for skinny data sets.
So technically, so technically it's an hour, but you can feel free to take as long as you'd like.
Okay.
It's up to you. You have carte blanche.
Okay. I mean, yeah, you guys are all in stage 4 lockdown, so.
Yeah, right. I have nowhere to be. Yes.
No, yeah. So okay, whatever you'd like. Okay, I was gonna let you pick, but okay. Let me tell you about. Then I'll tell you about things in order. Okay. So here's low rank automated machine learning. Okay. So this is kind of cool. We're going to automatically choose a machine learning model for our data set using low rank models. Okay. So here's the setup. Imagine that I've got n different data sets and I've got n different machine learning models. And I want to choose the, for a new data set that's going to come in, I want to be able to choose the best machine learning model that will give me the lowest error on that data set. Okay. What I'm going to do, this is you know, offline. I'm going to measure the error of every model on every data set. Now, obviously, that's very expensive, but I'm willing to do a lot of computational work up front so that when a new data set comes in, I can make a fast decision. I'm going to form an m by n data table A. Okay, so there's 1 row for every data set, and there was 1 column for every machine learning model. Okay. Okay, so now I'm gonna run a low rank model. So I'm going to find a skinny matrix X and a fat matrix Y, so that X times Y is approximately equal to A. And actually, since you know, what I measured was the error of every model on every data set, and that's a real number, actually I can just use PCA for this. Okay, the reason to use generalized low rank models is if I want maybe robustness to error, or if I don't want to actually measure every model on every data set. Okay. Now a new data set comes along, right? That corresponds to a new row in my data table on the left, and that corresponds to a new row in my X matrix over here on the right. Okay, now over here, right, if I wanted to know how every model performs on the data set, right, I might think I have to run every model on the data set, which takes way too long. I don't have time for that. Okay, but over here on the right, I say I only have, you know, as many parameters as the rank of my model. Okay, so here I'm showing 2, right, if this is a rank 2 model. Okay, so I only have 2 parameters to estimate. That means I only need 2 pieces of data to estimate them. Okay, so for example, if I ran, you know, at least 2, so maybe 3. So let's say I run 3 models on my data set. This one, number 2, number 3, and number 5. Okay, now to estimate this row of X, all I have to do is solve a least squares problem. Right? I want to find the X that when multiplied by matrix Y best approximates these 3 entries. Okay, so I can estimate this row of X. I can fill in my best guess, and then I can use that to impute the missing entries over here, right? Just by multiplying X, that row of X times Y. Okay, that gives me imputations for how other models would perform on the data set. Okay, so that's cool because suddenly I can say, okay, so now I think the best model on this data set is going to be the model that has the lowest imputed value over here. I don't have to run every model on the data set. Okay, so that's the idea of low rank automated machine learning. Okay, you can think of the rows here, rows of X as being data set meta features, the columns of Y are as model meta features, and the entries x times y are the predicted model performance on the new data set. Okay, so now the first question we should ask, this seems very pie in the sky. You could say, well, is automated machine learning really low rank? So one thing you might do is you might construct one of these error matrices running every model and every data set. In fact, we did this for all of the data sets in the UCI repository and all of the models in scikit-learn, gridding over hyperparameters. Okay, so a lot. I mean, you can look at the singular values of this matrix, and they actually decay quite nicely. Okay, so you wouldn't say it's, I mean, it's not exactly low rank, but, you know, even by the time you get to a rank 10 model, rank 20 model, you're doing pretty well. So now, actually, to turn this into a framework for automated machine learning, really the only thing we have to specify is which entries of that error matrix should we observe before we impute all the rest. Which entries are going to give us the most information. Okay, and here we can resort to really classical ideas in statistics. Okay, so essentially what we want to do is find this unknown vector x, right, which happens to be the latent representation of our data set. We are going to pick a set of measurements, yj, right? So these are the columns of the matrix y, right? And we know we're going to make, I mean, in our low rank model, right? We think that the measurements we're going to make are essentially inner products between x and yj. Okay, so we're going to pick a set of measurements yj for j in some set. And it's a set of columns that we're picking, the set of machine learning models we're going to run on the data set. Okay, we're going to measure according to this linear model, and I'm going to assume that there's some noise in this model. So this model is the misfit from my the misfit of the linear model x times y from the true error matrix A. Okay, so I'm going to model that as Gaussian. That's obviously a bad assumption, but it leads me interesting places. Okay. Now I'm going to estimate the unknown vector just using a least squares fit. Okay, so I use a least squares fit, and here's my estimate for the unknown vector in terms of the known matrix y, and it looks like this. Okay, so I can stare at this, and I can see that the expectation of my estimate x hat is equal to x. Okay, so I get the right value for the unknown vector and expectation, and the variance is equal to the sum of yj transpose over the entries that I selected, inverse. Okay, so so what does that tell me, right? So that tells me, you know, number one, right? If I selected more and more and more vectors to observe, more and more machine learning models to observe, right? This sum of yj transpose would get larger and larger, and so the variance of my estimator would go down. I'd get a better estimate for x. It also tells me that I better have at least as many yj's as the dimension of these vectors yj, which is the rank k of my model, right? Because otherwise this thing is going to be not full rank, and so it's not going to be invertible. And I guess the third thing it tells me, well, this is the variance is the matrix. Okay, that's not something I can like optimize or decide on, so I better scalarize that. Now, a pretty standard way to scalarize that is to use the log determinant. So what this says is I'm going to minimize the product of the singular values, right? Log of that. That's going to measure, right? So I'm trying to minimize the variance of my estimator. Okay, I'm going to select models to observe to minimize the variance of the estimator. Subject to, and here's maybe the interesting condition. So I'm going to put a VJ in front of, so VJ is going to be 1 if I selected that machine learning model and 0 otherwise. The total amount of time it takes to run all these models is VJ times T hat J, where T hat J is the estimated runtime of that machine learning model. So I'm going to put a constraint and say that the sum of the models that I select times how long it takes each model to run is less than or equal to tau. So this is my time budget. Okay. Subject to that time budget, I want the minimum variance estimator for my unknown vector x, right? The unknown latent vector that represents my new data set. Okay. Now this is a challenging optimization problem to solve. We've looked at two different methodologies for solving it. One relaxes this to a semi-definite program by replacing this constraint with a constraint that Vj be anywhere between 0 and 1 and then rounding. The other uses a greedy algorithm, so we add one component Yj at a time. Doing that in order to maximize the increase in log debt, since the the log debt objective, the negative of what I'm showing here, since that's submodular, that actually you can get a guarantee on how well the greedy algorithm performs. Okay. Okay. So. Right. So actually, one interesting challenge is estimating the runtime for each of these machine learning models. And I guess what's kind of interesting is that using a polynomial regression on the number of data points and number of features in the model, you can estimate the predicted runtime to within a factor of 2 pretty well. So here I'm showing you all these different algorithms for machine learning. The 2 black lines show you which ones we predicted the runtime within a factor of 2. And you can see that for most of these data sets and most of these algorithms, we were able to predict the runtime within a factor of 2. Kind of neat. Okay. So the resulting system, we called it OBO. And you can ask, does it actually work to find good algorithms for your machine learning models? Good machine learning models for your data sets? And the answer is yes. So we compared this to a state-of-the-art system for AutoML, which is this blue line, AutoSKLearn. Our system is called OBO, so that's the red line. We also compared it to a version of OBO that instead of using the sort of clever method for selecting which machine learning models to observe, just observes a random set of models that's predicted to finish within the runtime. And so what you can see is that actually the random version does pretty well. OBO does the best. And AutoSKLearn is not able to return any sensible answer in less than 16 seconds on these data sets. Okay, so we're able to make very good predictions on what models will work best on your data set very quickly. And so notice it, right, since we've gridded out hyperparameters, we're doing simultaneous model selection. So selecting between things like, should you use AdaBoost or decision trees or gradient boosting or Gaussian naive Bayes, and also what value of the hyperparameters should you choose? So this is often a major pain point in machine learning workflows, is just like the cross-validation takes forever. So you'd be a lot happier if you didn't have to do that. Okay, so the answer is you don't have to do that. Okay, there are better ways of thinking about this. Okay. I think I should probably mostly skip over why low rank. Okay, so I think all I want to tell you here is that all I want to tell you here is that if your data table, right, so you could say, why I showed you lots of examples where the low rank models did very well, and yet it's not obvious why that data should be low rank or even approximately low rank. Okay, so we're motivated by this to come up with a much more general theory about why so many data sets are low rank. So we have some assumptions that I'm showing you here on how a data set might be generated. These are pretty general assumptions. Basically, they say that for every row, you generate the row, right, latent variables for the rows from some distribution, generate latent variables for the columns from some distribution, pick some function that's analytic that takes the latent variable for the row and the latent variable for the column and produces the value you observe. Okay, plus a tiny extra assumption that's not very important. Okay, so so that's your model for data generation. It's called the latent variable model. So if your data table is drawn from a latent variable model, now it's not generally going to be low rank, generally going to be full rank. But we can look at the rank of an epsilon approximation to that data table. Okay, so I'm going to look for a matrix that's every entry of that matrix is within epsilon of the corresponding entry of my data table A. And I want to find a matrix like that that has low rank. How low a rank should I expect to be able to find? And the answer is that the rank that I need should grow as log of the number of rows plus number of columns divided by epsilon squared. Okay, so what does this mean? If I want a really, really accurate approximation, low rank models are not going to work very well, okay? Because I've got a 1 over epsilon squared. That means if I want, epsilon equals 0.1, no problem. If I want epsilon equals 0.001, then get out of town. Okay, the rank's going to be really high. Okay, but this is really interesting. Okay, log of m plus n. So that says that as my right. So remember, like the naive bound for rank, like any matrix has rank that's less than or equal to the minimum of the number of rows plus the number of columns. Sorry, minimum of the number of rows or the number of columns. Okay, so the naive bound for rank grows linearly in min of m and n. Okay, but here what I'm showing you is the rank grows as the log of the number of rows plus the number of columns. Okay, so what that says is that as your data table gets really, really, really big, as long as it stays kind of square, right, this is going to look much smaller than the naive bound of min of m and n. Okay, so your data table is going to look approximately low rank, and more approximately low rank as it gets bigger, as long as it's getting bigger in a kind of square way. If it's getting bigger but it's kind of skinny, then this bound doesn't tell you anything. Okay, because the minimum dimension is actually pretty small, and so the log of m plus n will easily get bigger than the minimum dimension, which is staying constant. Okay, so you should expect large square data sets to be low rank. You should not expect large skinny data sets to be low rank. Okay, so that motivates my sort of the last thing that I want to tell you about, and here I'll be quite brief because we're you guys have your stage 4 lockdown to get back to. Okay, so what I've told you is that large square matrices are often low rank, but skinny or fat matrices are not. So what do we do about skinny or fat matrices? We should not expect generalized low rank models to work well. Okay, there's no theoretical reason, and in practice they don't. Okay, so you might want a different kind of model. So I guess the thing let me think about the skinny matrix the skinny matrix setting. So in that setting, I have a lot more information about the columns than I do about the rows. Right? The rows I just have a small amount of information, but the columns I get more and more and more and more and more information. Okay, so I should be able to fit a more sophisticated model to the columns than to the rows. Okay. Okay. So how am I going to take advantage of that? Here's what I'm going to do is I'm going to look, it's the same kind of setup. Given an m by n data table A, I'm going to look for a low dimensional vector z for each row, and I'm going to look for a function for each column. So the aij is approximately equal to that function, the jth function, applied to the ith vector zi. Okay, so there's this asymmetry. So what I showed you before, that function was just a linear function, right? Y transpose. Okay, now I'm saying I'm going to look at more general functions. Okay, because I have I have more data about every column, right? So I can use all of the data in that column to estimate the function fj. Whereas for a row, I have less information, so I better set my sights low and just estimate a low dimensional vector for every row. The interpretation is kind of the same. The zi and fj are compressed representation of my data table A. Zi is a point associated with example I, and now fj is a function associated with feature j. Okay, so there are a couple of examples that are worth talking about. So if f is just the inner product, right? So f of z is z transpose y for some fixed y, then this high rank model reduces to a low rank model. If z is low dimensional and f is a polynomial function, that's okay. What I have is a model for sort of low dimensional manifolds. And there's a third model that I want to talk about, which is when Z actually follows a Gaussian distribution, and F consists of monotonic functions. So that's called the Gaussian copula model. Okay, so polynomial models sort of have this kind of story. You know, your data here the original data is these red points. So you can see it comes from a one-dimensional manifold that's embedded in a three-dimensional space. If you impute it using low-rank matrix completion, what you get, here so you can initializing the data with zeros to get these blue things. If you try to recover this with low-rank matrix completion, the blue circles over here are what you get. So you see, you do not recover the original data. But if you try to reconstruct this using a method that sort of understands about this polynomial structure and exploits it, which we call kernel factorized matrix completion, then you can actually exactly recover the original data. Okay. So that's pretty cool. And here you can see the setting, right? I'm in 3D space, right? And I have a lot of data. Okay, so number of rows is like 100, and number of columns is like 3. Okay, so I can do much better on structured data like this, using a high-rank model than a low-rank model. Here is sort of my last example. So this is the Gaussian copula model. Okay, so the Gaussian copula model, this is also, by the way, a pretty popular one for multiple imputation. Peter Hoff had a paper on this from 2007 so it's used for multiple imputation, including in the social sciences. So our recent work with my student Yishuan Zhou speeds up Peter Hoff's method, so it's actually usable on much larger data sets and can be fit much faster without any hyperparameters. So it becomes much more usable. So here's the model. Your low-dimensional vectors are drawn from a normal distribution with some covariance sigma, and the observations are generated by some entry-wise monotonic function of that sigma. So in pictures, here's what it looks like. You imagine that the underlying data, right, the sort of underlying latent structure is actually just a Gaussian structure. But then your observations have done some horrible non-linear thing to it. So for example, one horrible nonlinear thing you might do is truncate. Okay, so if the data is above this line, this dashed line, then you truncate to value 3. If it's between these two dashed lines, you truncate to value 2. And if it's below this line, you truncate to value 1. Okay, by the time you do this in both dimensions, so I'm going to truncate the x coordinate as well as this y coordinate, I've actually truncated to just 7 distinct points. And if, for example, I was interested in the correlation between my first coordinate and my second coordinate, I've totally distorted it, right? The correlation between the real values is 0.8. The correlation between these truncated values is now down at 0.5. Okay, so I've broken things. Okay, so you can use the Gaussian copula model to reconstruct this original correlational structure and sort of understand the relationship between your variables and also do better imputation. Okay, so just to show you how well this works, we looked at a sample of the movie lens data set. This is a pretty classic test data set for low-rank matrix completion. It models essentially the Netflix problem. So there's one row for every person who watches, who rated movies, and there's one column for every movie. And the entries are so mostly missing. But if that person rated that movie, then you know their rating. So the rating is either 1, 2, 3, or 4 or 5 stars. Okay. So we took a subset of that data set that consisted of all 207 movies that had at least 1,000 ratings. And every user who rated at least one of those 207 movies. Okay, so this was, I think, 10,000-ish users. So a very skinny data set. 75% of the data was missing, and we masked an additional 10% of the data to see how well our imputation method worked. Okay, so we compared to a bunch of other imputation methods. And our new proposed sort of copula EM model is able to recover to perform imputations to have much lower error than all of the other models, both in mean absolute error, also in root mean squared error. Okay, and I think what's particularly notable about this model, and because I'm, at the end of my talk and not telling you much about it, I'm just gonna have to tell you instead of showing you. What's really notable is that the model has no hyperparameters. Okay, so whereas for almost all of these other models, there's something that you have to tune, right, that takes extra time because you have to try the model for each value of this parameter, right, and try to find the right one. This copula EM model has no extra hyperparameters, okay, because it's pretty neat compared to generalized low-rank models. In generalized low-rank models, the one really annoying thing is that you have to select those loss functions, and the loss functions that you select affect the quality of the theta. I showed you that in the hospitalization data set. Okay, so the copula EM model gets around this. You are learning effectively the loss functions from the data distribution itself. Okay, so that's actually super powerful. Now, whoever cares about missing at random versus missing not at random versus missing completely at random is going to be disappointed that it also makes the copula EM method much more sensitive to violations of your missingness assumptions. So the copula EM method can go more horribly wrong when your data is missing at random and not missing completely at random. Okay, but with that caveat, has no hyperparameters. It's pretty great, worth trying out. Okay, one last issue that I want to sort of highlight. So among these, models that all perform pretty well on the movie lens data set, the generalized low-rank model uses rank 8. The soft impute model, which is essentially using quadratic loss, the best rank after cross-validation is rank 99. And the copula EM model is using a full rank covariance matrix. Okay, so what is the rank of the data? Would you say this is really low rank data? Right? I mean, these different models, right? So the fact that there's a best rank, corresponding to each model does not mean that the data really is that rank. So I would say that all of these are different sort of approximations as to what's really going on with the data. So in summary, big data is, okay, approximately low rank. I showed you examples in social science, in medicine, and in machine learning. And I showed you how to exploit low rank in order to fill in missing data, reduce dimensionality, and in some sense, turn big, messy data into small, clean data. So thanks for your attention. Would love more questions.
Thank you so much. So we actually do have a couple of questions that that people put up, and then also I just want to say that if anybody wants to raise their hand, there's a way that I can kind of recognize you, and then and I think your video will pop up, or at least your audio will.
I think it's also worth saying, if I were giving a talk actually in Melbourne, I'm sure I'd have a day of visits and I'd get to meet with lots of you and chat about your research, and I would love to do that. Just send me an email. Let's take advantage of the fact that we're, right. I'm just as far from where you live as any of your colleagues right now. Okay.
That's very gracious. So let me at least read two of these, and the first one is, does A, the matrix A, have to be non-negative, like in non-negative matrix factorization?
So in general, no. If you, in fact, you can even ask for an approximate non-negative factorization of a matrix that does have negative values, though that's a little bit of a strange thing to do. Usually when you're asking, so to ask for non-negative matrix factorization, the way that you do that is by using the non-negative regularizer. Usually people would only do that if the matrix that they're A is non-negative, but you can do it more generally if you want to.
Okay, great. And then the next question is, it reads, in some analyses, say regression, the variance of the feature after imputation is important. Do variances tend to be over or underestimated by GLRMs? And how does the variance estimates compare to imputation to be a supervised approach?
Yeah. This is such a great question. So, so this is why in the work that we've been doing on the Gaussian copula models, we did a lot of back and forth, and actually I argued with my student a lot because I really like the generalized low-rank models framework, and he's more of a statistician and was really promoting a more, okay, so the variance is underestimated by generalized low-rank models. And the reason for that is that you're imputing the missing data with the mean, right? So the correlations you end up seeing end up being higher, and since you're imputing with the mean rather than adding in the observed variance of the column, you're going to end up with imputations that have lower variance. Now, if instead of imputing with the mean, you actually sample from the posterior distribution, you can correct for that problem to some decent extent, but it still might overstate the correlations. Now, if this is the kind of thing that you care about and you think this is very important, I might suggest that you choose the Gaussian copula model instead, which has a stronger statistical foundation, and can make sort of better guarantees on things like recovering the true covariance matrix of the data, assuming you have missing completely random data.
I'm muted. Anybody else? So somebody's asked, can we make the slides available? Is that okay?
Yes, yeah, I can make the slides available. I'll send them to you.
Okay, great. And there's a new question here.
Yeah, one other thing worth saying about the Gaussian copula model, because I didn't say it in my talk, you can't use so Peter Hoff has a beautiful R package for fitting these using an MCMC method. That does not scale to large data. You just can't use it for large scale data. We have so in addition to what I showed you using the EM method, we have a version of that works for a low rank Gaussian copula model that does scale to arbitrarily large scale data. So we can handle, for example, the entire movie lens data set of 10 million observations. Okay, so tens of thousands by tens of thousands, no problem. Okay, so so there's no trade-off between low rank and these other nice properties of the Gaussian copula. You can actually get both. I think the main nice property there is the fact that it doesn't misstate the correlations. It's sort of more reasonable to do multiple imputation from, and it has no hyperparameters to choose.
That's great. So the next question is, rank is not a continuous function of matrix elements, right? So isn't any other alternative objective function to minimize a continuous approximation of rank, or, and then there's an ellipses. Let me see.
Okay, so let me talk about completely observed matrices that are real valued, okay? Because those are the ones where it's reasonable to talk about the rank of that matrix as the quantity that you might care about, okay? So you can ask, what is the shape of the set of low rank matrices? Okay, the set of matrices of rank less than or equal to k, okay? And that is it's a k-dimensional, this is a k-dimensional manifold. And so it means that if you're in a much higher dimensional space, you can step off the manifold with like epsilon perturbations in any direction. So you can perturb any entry of the matrix epsilon, and suddenly it's you can get to you can even get to a full rank matrix like immediately. Not by perturbing one element, but by an epsilon perturbation of the matrix itself, you can get to a full rank matrix. It's true that now in the framework that I was showing you, I wasn't penalizing the rank of the matrix. I was constraining the rank of the matrix, okay, by insisting on the dimensions of x and y. So by construction, x times y in my framework is always exactly rank k or less. So the thing the compromise that I'm making is, my matrices that I'm getting are exactly low rank. I'm saying I'm not going to exactly hit the observed matrix. I'm going to get an approximation to the observed matrix. Okay, so if you perturb the entries a little bit in a way that, you know, moves away from low rank, well, I'm just not going to catch that perturbation. My error is just going to increase. Okay. And the other compromise that's introduced by moving to this low rank parameterization is the fact that I can't globally optimize these models. Okay. Many of these models, right, there's a sort of a whole another way you can approach this, which uses convex relaxations of your objective. In that case, you don't guarantee exact low rank, but you can guarantee things like global optimality. I hope that was an answer to the question.
That's great, thanks. So I made Sybil, who asked the question. If you want to ask a follow-up,
you can unmute yourself.
Yeah, you're more than welcome to unmute yourself. No? Okay. All right, well, thank you so much for this. We really appreciate it. So Sybil says, thank you. It was a joy to listen to the talk. We really appreciate it, and we'll make this available on the YouTube channel. And that's very gracious of you to offer to answer questions or engage in some follow-up discussions via email. Thank you so much, Madeleine, for your time and for your excellent work. We really appreciate it.
Yeah, great getting to chat with you guys, and I wish you the best of luck in stage 4.
Yeah, you too. Good luck in November.
Well, we don't even have stage 4. We're just wandering around coughing on people.
Yeah. Well, right. And so good luck in November, right?
Thank you. Okay. Take care.
Thank you.